I'm Philip Nelson. I just want to tell you a little story about pattern formation in an active fluid as a prologue to Alan's talk. So, surely you have all seen video micrographs of embryogenesis, an amazing, immaculately choreographed dance in space and time. You can watch those videos over and over and see something new every time. But how could anything like that possibly happen at all? Is the question you're always left with a video like that. There's quite a lot going on. Nobody has a quantitative predictive model that explains everything about embryogenesis. So therefore, now is a good time in your career to start thinking about it before it's all solved. At the very least, you see cells crawling over each other in some purposeful plan to create a body based on something in their genetic code. So we call that morphogenesis, or the birth of form. But who is the conductor of that orchestra? How do the cells know what they should be doing? In physics classes, we talk a lot about development over time, but not so much about space-time. And of course, by the way, lots of people care a lot about the failures of embryogenesis. Anything that you could learn about this could have potential implications for human health. It's an important reason to study the field. So you're going to hear some significant progress today. I'm the warm-up band, and then Alan Rodriguez and Amy Shire and their co-authors are the main act. So before really getting going, I got a little subtext to reveal to you. I like to teach biological physics. And as I used to say on transatlantic flights, the ignorant student who I need to enlighten first is myself. And I have a lot of difficulty with this subject. Had a lot of difficulty. I keep falling in love with something or other. There's this explosion of interest in important results. I'd like to teach them, but I always get stuck because there's always something that's technically daunting that I can't get across to students. Sometimes the mathematics gets out of control. Sometimes there's too many biological details that have to be acknowledged. Sometimes it's hard to justify the model. I've never been able to do this until this year. Okay, so the story I'm going to tell you today is simple, maybe seem even trivial depending on your background, but that's precisely what makes it so precious and hard to find in science and worth trying to get across to students. Okay, so I'm going to show some images from work by Alan and Amy. Here's a chick embryo, and on day 6, its skin is roughly undifferentiated. You've got no particular pattern in it. 48 hours later, there's a pattern. The pattern are cell clusters that are primordia. Primordia are going to become follicles. The follicles are going to become feathers, and they're not perfectly random. If they were perfectly random, there'd be bare spots, and that's not adaptive. So they have some definite spacing. They start in a line and move outward from that line. And here's your basic pattern of morphogenesis. Where does that pattern come from and how? And in their article, one of their articles, they start out by saying, before follicle formation, you've got this undifferentiated thing. How this leap in complexity is reproducibly initiated remains unsolved. Okay, and then they pointed out that previous studies have all been saying, oh, it's a Turing pattern. It's always some morphogens that get laid down chemically, and then cells respond to that. We began to question this model when we discovered that in the avian skin, follicle fate markers don't precede the earliest architectural changes. At day 7, you're starting to see those architectural changes and still no chemical fate markers. So maybe something else is going on besides what's always been assumed. So in the great physics tradition, they then proceeded to build it to understand it. And what do I mean by that? Well, this is a complicated system. Got a lot of cell types, a lot of stuff going on. Strip it down to the bare essentials that recapitulates the pattern that you're interested in understanding. So what are the bare essentials? Well, instead of a whole lot of cell types, one cell type, just dermal cells. So now there's suddenly no question about communication between epidermis and dermis. There's only dermal cells, and they're sitting on just a collagen matrix, completely stripped down system. And they get laid down. The experimenters lay them down in a ring. A ring is a line that's been wrapped into a circle, so you don't have to worry about boundary conditions. And they lay down in a uniform density. And here you see 20,000 of those cells. And what happens over 48 hours? Amazingly, it recapitulates the formation of the primordia that you see in the real chick embryo. Okay, so just that system is enough to create the pattern formation qualitatively, but also quantitatively, the spacing and the timing, all pretty much like the real chick embryo. This is a good model system. So what can happen? Well, we know that cells are contractile. They can pull on their surroundings. And when I say pull, I mean a force like Isaac Newton kind of force. And that force can make other cells migrate. And when cells migrate, possibly they might bunch up. And when they bunch up, that would amplify the pulling force. And amplifying the pulling force gives you a feedback loop. And interesting things can happen when there's a feedback loop. So that's the big idea. As they say, a mechanism whereby self-organization acts as the regulatory step for initiating morphology as well as gene expression, and not the other way around, has received less attention. Okay, feedback, yes, can lead to interesting phenomena, but that's kind of qualitative. We got to do a little better than that. And first of all, we're noticing there's a large number of identical actors. There's 20,000 of those cells, and they're all the same cell type. Makes us suspect that for their aggregate activity, we might win by neglecting the individuality of the cells and instead looking at their local average density, average velocity, things like that we physicists are good at doing in fluid mechanics. And when you make that continuum approximation, then also the intrinsic randomness recedes. It's there bundled into constants like the diffusion constant, but you don't have to deal with it. Okay, that's a characteristically physicist style gambit I think is worth teaching to students, which is what I like to do. After all, when you turn on the tap, water comes out. You don't have to worry about the fact that the water is made of individual molecules. It's not relevant for many purposes. You're not have to worry about the Brownian motion either. So let's think about a continuum model of an active fluid. But why should we model? What's the point? We had a nice idea. It inspired this great experiment, came out as suggested. Aren't we done? Okay, we got to say that to students as well. Well, you know, we can say, well, we're trained as physicists. That's what physicists do. Okay, we can do better than that. We have to do better than that. Because some cartoons seem convincing, but they just don't work. I mean, by that, there's no quantitative instantiation that has the properties suggested by the cartoon. You got to check that. Or often the model will work, but only in some limited parameter regime. That may or may not describe the biological system of interest, or it may sometimes yes and sometimes no. There could be a bifurcation, a change of qualitative behavior as parameters are adjusted, and that's worth knowing about as well. And finally, there are too many cool ideas and too many cool experiments you could try and not enough time and money to do them all, so modeling can help you to design your crucial experiment. That's why we model. Okay, so here's a Chinese fortune cookie I got, which I'm sure is really relevant to this talk. All I have to do is figure out what it is. We'll just keep it in the back of our mind as we get back to work. Okay, so we've got some words. Let me have some more detailed words. After the detailed words, then there's going to be some cartoons and there's going to be some formulas. That's the usual workflow. So I'm going to regard this system of cells plus matrix as some compressible continuous fluid. It's got some density I'll call rho and some flux I'll call J, and then there's surrounding water that's only going to be implicitly present in the model. Okay, over the course of the experiment, the cells are not dividing, they're not dying, that's a fact. So our fluid is conserved, but its density isn't necessarily constant. After all, the cells and their matrix can cram together, expelling some water. The cells and their matrix are a compressible fluid. So there's no gas pressure, the cells aren't crammed up touching each other. But there can be friction. There can be friction both against the substrate that it's all sitting on and also with the water that has to be squeezed out if the density is going to increase. Okay, so these are ingredients we want to turn into symbols and formulas. Furthermore, these cells, they're actively pulling on the surrounding matrix. That surrounding matrix in turn transmits the force to other cells. That's the contractility that I talked about. The force per volume is proportional to the density of cells. So there is something like a pressure, but it's a negative pressure. Okay, if you want to say, oh, that reminds you of pattern formation in the early universe under gravitation, okay, you can go ahead and say that, but we don't need to say that for this talk. This contractility is also opposes dissipation. It's active, could possibly counteract the dissipative character of friction and cause structure to grow instead of decaying. Okay, so that sounds good, but I want to walk you through the model in a little greater detail because every single minus sign in those equations is critically important, and it's just necessary to understand where they came from. So, okay, we're going to regard the cells plus the matrix as some highly compressible fluid with some density and some flux. And here's the first cartoon. If the flux on the right-hand side is smaller than the flux on the left-hand side, then there's more entering than there is leaving this little slug of fluid, which means there's going to be a pileup and the density is going to increase. So, okay, a negative gradient of the flux leads to a positive time derivative. That's one of the minus signs that was important to get right. I'm going to call that conservation. Okay, second of 4 cartoons. What if the density isn't constant? Well, there is Brownian motion, and if the density is greater on the right-hand side than on the left-hand side of this slug, then there's going to be a flux to the left trying to erase that non-uniformity. So that's my second equation, which I'm going to call transport. It's the second term, and I explained the minus sign. Then also, if the fluid is flowing, there's just going to be transport, advective transport. That's the first term. Okay, 2 out of 4 cartoons. Here comes the third one, starting to get a little bit more tricky. The fluid is exerting force. At any point in the fluid, the entire right-hand side, everything to the right of that point is exerting a force on everything to the left of that point, which I'm going to call stress. Okay, that's what I mean by stress. And the stress might not be uniform. If the stress is greater on the right-hand side than it is on the left-hand side, then this slug of fluid has a net force on it, and that's going to make it go. It's going to be opposed by friction against the substrate. So I've got a force balance equation. If the stress has a spatial gradient, that's going to lead to a velocity with some friction constant against the substrate. Okay, and the fourth of 4 cartoons, what if this fluid is stretching out? So here I've imagined that on the left-hand side, velocity is moving left, and on the right-hand side, the velocity is moving to the right. That's going to stretch the fluid out. Water has to rush in because the system's incompressible. That water rushing in is going to make a viscous drag, which is going to tend to oppose this motion of the fluid. Okay, so the left-hand end of this slug is getting pulled rightward by the right-hand side. So if my fluid is in extensional flow, then I'm going to get a positive stress. That's the last of those critical minus signs I told you about. So I'm going to write all that by saying a gradient of the flow field is going to lead to stress with some viscosity coefficient I'm calling eta. On top of that, there's another contribution to the constitutive relation due to the contractility. So each cell is pulling. Total force per unit length on this one-dimensional fluid is proportional to the density, with some constant of proportionality having to do with how contractile those cells are. Okay, so that's the model. Model consists of those equations inspired by those cartoons. But oh my God, it's partial differential equations. It's 4 partial differential equations. How are we going to do that? It's so complicated. Okay, so we have a trick, and the trick is Fourier analysis. If I can figure out what's happening to sinusoidal variations, then I can take any initial condition I want and express it as a sum of sinusoidal bits, evolve each one of them by its own simple dynamics, and then reassemble them after a certain amount of time has gone by. If I have a handful of sines and cosines, I can get an approximation to a square wave like this, which has low density followed by high density. If I have 1,000 sines and cosines, I can get an excellent approximation. So that's going to be the key to getting out of the world of partial differential equations. I can convert them into ordinary differential equations by mode decoupling. Okay, how does that work? Well, let's start with something we know about, which is diffusion. You can take a periodic initial density pattern, express it as a bunch of sinusoids, use the linearity of the diffusion equation to let each one of those modes each one of those sinusoidal modes do its simple exponential evolution, and then reassemble them afterwards to get what the profile will look like at later time. And okay, I did that. And these colored curves show just what you expect from diffusion. The sharp boundaries are getting softened and rounded off. The total amount isn't allowed to change because of continuity, but the exponentials are easy to deal with. And I can just blast right through the step of ordinary differential equations, because if a solution is an exponential, every time derivative is just a factor of the growth rate. So my equations turn into just algebraic equations. Each mode has its own algebraic equation that determines its growth rate. From the growth rate, I apply that to each of the modes, reassemble them into the final resultant, and that's how I got these curves. Okay, great. Diffusion erases structure. We knew that. Not surprising. But now we're ready to ask about active fluids. Will there be any modes with positive growth rate? And if so, which ones? That's the key. Okay. Here's some notation I already introduced, so it should all be on the same slide. There's a conservation law. There's transport of cells. All those should be partial derivative signs, sorry. There's a constitutive relation. And the transport of cells has this important feature of nonlinearity. Okay, nonlinearity is your signal that something interesting is going to happen. The constitutive relation has an important property that it's got a flux of energy going into it. Flux of energy is what allows you to potentially overcome the effects of diffusion. And then there's the force balance equation. And okay, now we have some tricks that physicists know how to do, and I'm not going to go through every little bit, but it's better to write all the quantities, all the dynamical variables, all of the parameters in non-dimensional form. Then the beautiful thing you get is that though there are several parameters, they only enter in two non-dimensional groups. Okay, the whole qualitative feature only depends on two parameters and not a lot of them. First one's called Peclet number, has something to do with the contractility. The second one is some viscosity parameter, has to do with the relative importance of friction against the substrate versus viscosity in the fluid. Those equations can be written in terms of non-dimensional variables and these non-dimensional parameters. And now you have a not very difficult space of things to try. Okay, so you expand the equations in their modes and apply linear stability analysis, which I don't have time to do in great detail, and ask yourself, for various choices of the contractility, what's the fastest growing mode going to be? And so here's a graph that I just reproduced out of the supplementary information of that paper. At low contractility, that's the bottom curve, every mode is stable and there's no pattern formation, and it's just like diffusion. Okay, as you increase the contractility though, some modes become unstable, and the peak of each of those curves, the most unstable mode, that's going to be the one that's going to dominate at long enough times. Of course, at very long time, then the nonlinearity is going to kick in, but at intermediate times, the ones to look out for are the most unstable modes. That's our prediction from this model. Okay, it's a promising theory. It has only a few parameters, and crucially, those parameters can be independently controlled experimentally in a way that lets you test whether the model is capturing the behavior throughout all the parameter space. If it is, that's probably not a coincidence. So, quoting those authors, when we inhibit contractility with blebbistatin, we get a change in the pattern in our experiment that whose trend was predicted by the theory. Conversely, when you add caliculain A, that amplifies contractility, and then you get the opposite effect. So that's great. That's one of the two non-dimensional parameters. They were able to vary the other one as well by just changing the viscosity of the fluid by adding some ribose. Okay, so a limited parameter space, the ability to independently control each of the parameters and see what happens. This is an experiment that would be very falsifiable. All right, so there's some experimental data at the top. On the left, there's some theoretical predictions on the right. And okay, as you change the contractility, you get the expected qualitative behavior. As you change the viscosity parameter, you get the expected qualitative behavior. They also presented here at the bottom row some photomicrographs at various still frames when they're video photomicrographs, and results of their simulation presented on a grayscale to look like the micrographs, yeah, it's working out. It's working out well. But there's more. Quoting those authors, moreover, our experimental observations confirm the predicted timescales, not just the spatial patterning scale, but also the timescales and how they change with both of those manipulations. Okay, that's another piece that was not added in by hand. It's either going to succeed or fail. Okay, so that's the experimental end. Stepping back, once again, I like to teach things. Everybody is familiar with the idea of shear viscosity in an incompressible fluid, like honey or motor oil or something like that. Fine, we understand that. How can there be viscosity in one dimension? It took me a while to get my head around it. There's no shear in one dimension. It takes an active imagination to conceive of the possibility of compressive viscosity, because the only compressible fluid we ever deal with in everyday life is air, which has no negligible viscosity on human scales. Okay, so we don't experience it, but through the lens of mathematics, we can find that it has to be there. That's a place where the physics viewpoint is helpful. Mathematically, you enumerate every contribution to the stress consistent with the symmetries of the problem, and there it is on the menu of things that's allowed. Okay, something worth teaching. So I'm running low on time. Let me put it in a nutshell. Yes, morphogens are important, but not all pattern formation is Turing or even morphogen driven at all. Some, like in this case, everything was entirely mechanobiological. It's a new paradigm that's coming out. Moreover, as those authors said, rheological phenomena in development and disease have yet to be applied to a study of non-trivial morphological changes in vertebrates driven by mesenchyme. Okay, a wide open field. Okay, but something maybe is still missing. I've given you these symbols, I've given you these cartoons, I've given you graphs, but come on, this is a story about dynamics. Why don't we represent time as time instead of like some axis on a graph? Okay, it's a story, it should have a beginning, a climax, a denouement. Okay, so here's a little thing I asked my students to prepare. There's a random initial condition of density on a circle, and what do we expect? We expect to see most of the modes getting crushed because they have negative growth rate, a few growing, and ultimately dominated by the fastest growing mode. We should start to see a pattern forming, and oh, there's an animation that that shows you those things you want to see. Okay, I've just got a little bit more subtext here. Physics, what is it? It's not just formalism. It's about mobilizing formalism to bear on real phenomena and going from one understood phenomenon to one you wish to understand, mediated by formalism. That's what physics has to offer. Oh yeah, but we want it to be true, we'd like it to be useful, but is it beautiful? Physicists want things to be beautiful as well. Well, what is beauty? What is beauty? Well, here's G.H. Hardy. High degree of unexpectedness combined with inevitability and economy. Sonia's nodding. Maybe it's also the description of that click you feel when the seemingly unconnected ideas merge into one framework, or the bones of abstract ideas get clothed in the flesh of real phenomena. Does this story got that? I don't know. You decide. Thank you.
Well, let's thank Phil for this really, really wonderful talk. So I see a few questions in the chat. And actually, there's already an active discussion going on in the chat. So maybe, Phil, you want to answer those questions. I'm going to read it out. So Marco says, is there a simple way to include the emergence of flow in the pattern as well?
The solution includes the flow field. I did display it, but it's there in the solution. What leaps out at you in the micrographs is the density. So I was showing you the density, but it's there all along.
He said he meant a global flow.
You could certainly imagine an experiment with markers that you watch by particle velocity velocimetry, so that those become available to you. And then I think you have to find conditions where a global flow is going to happen. This bunching up has flow that's alternating, and isn't global. So you'd have to find an experimental situation where you would expect global flow to be happening. Alan might be able to address that as well.
Okay, so
Let's see the nonlinearity in the rho times v. Well, that's the product of two dynamical variables. So therefore it's not linear, it's second order.
okay. And Miranda just asked, thank you for a very interesting talk. In the model, there's one velocity. Is there an assumption that the velocity of the cells, the ECM, and the water are the same, perhaps due to large friction between them?
Okay, certainly there's an assumption that the substrate isn't moving. So velocities relative to the substrate are meaningful. Water isn't appearing explicitly in the model at all, so its velocity isn't in the model. And we are assuming that the cells in ECM are being carried along together. And yes, I can imagine decoupling them, but I haven't seen that attempted.